I would like to invite our next speaker, who is Aliaksei Horlach. Aliaksei is a first-year Azrieli Fellow who comes to us from the Department of Nanotechnology and Nanoscience at the Technion. His topic for today is Let's Shed Light on the Electron Microscope.
Thank you, Rochelle, for the introduction. And I will start my talk. I hope you can see the screen and everything is fine, right? So, okay. Hi, my name is Aliaksei, and let's shed light on electron microscope. I will start my talk with an example. The whole world nowadays is fighting with coronavirus. Probably you heard that some of the vaccines against COVID are using nanobiological drugs. If in a couple of words, such vaccines are made of specific biological molecules wrapped in a coating. The size of one particle is 100 nanometers, which is in 10,000 times smaller than the needle of syringe. It is a really small size that even hard to imagine. But how people are able to construct and to image at such small scales? One possible way to go into such a small scale is an electron microscope. Electron microscope can image small biological molecules, viruses and bacteria, helping to investigate their nature. As I mentioned before, it helps to image and design nanodrugs, such as COVID vaccine. With the electron microscope, you can zoom in even more and really see the atoms, the smallest building blocks of the matter, which size in 1,000 times smaller than the nanoparticles used in vaccine. These unbelievable capabilities of electron microscope make possible to image and to study entire microscopic universe that was before completely hidden from our eyes. Amazingly, all these pictures you can see here are done using electron microscope. But how this unique device works? Electron microscope in the top produce electrons, small particles that we will discuss later. These electrons interact with the biological molecules we want to study. This interaction is a keystone in the electron microscopy. In a simple words, if the electron interacts with the molecules, it gives a white pixel on the screen and a black pixel if it didn't interact. We display many pixels, which finally forms an impressive image. What we saw before, all the biological molecules, nanobiological drugs, atoms of nanometer size. Everything of such small size is quantum and belongs to world of quantum. This world is different from anything what you can see in everyday life, having unique rules and patterns. An electron microscope is our guide in the world of quantum, in the quantum realm of matter. But there is another quantum realm of light. And up to now, nobody could truly look into it, image it with an electron microscope. What I showed before is how we can immerse in the quantum world of matter using electron microscope. And now we're going into my research. What I will show is how to use electron microscope to step in the world of quantum light. We want to investigate quantum world of light because it has a lot of interesting applications that seems as a science fiction. For example, the quantum properties of light help to detect very sensitive events, such as gravitational waves, from the objects at billions and billions of kilometers from Earth. Special properties of light can be used to build completely secure channels of communications that nobody would be able to listen to your conversation. The quantum computer based on quantum light can be more efficient and powerful than millions of classical computers brought together. But how do we suggest to study light and its wonderful properties? To answer this question, let me start with the explanation of what is light and what are the electrons. If we will zoom in the light, for example, emitted by lamp, on the fundamental level, we will see that it consists of photons, elementary particles that transmit the light's energy. If we will zoom in any material, for example, in gold, we will see that it consists of atoms, and each atom consists of positive protons and negatively charged electrons. So now let's collide electrons and photons and let's see what will happen. The main problem is that photons don't like electrons and just scatter from them. So what we try to do is to force them to interact. But how to make the photons to interact with electrons? The idea is very intuitive. We just need to tie the photons up so it does not run away from the electron. Then electron can interact with such photon. But what electron can do with this photon? It appears to be really similar to the relationships. Firstly, the electron can be indifferent to the photon and does not interact with it. Secondly, everything can go wrong, and due to the interaction, the electron can get upset and his energy will decrease. Thirdly, the electron can enjoy the interaction with the photon and in this way increase his energy. If we now consider interaction with many photons, it forms such triangle. Interaction with each photon has three possibilities as we discussed before. Here we can see one of the possible rows of electrons after the interaction with many photons. The bins below define the final energy of the electron after the interaction with many photons. If we launch many electrons, they will occupy different energy bins. Like in real life, the majority of electrons will stay indifferent after interaction. But some of them will be more energetic and some of them less. This distribution of electrons in bins is called electron energy spectrum. This process is very similar to the Dalton board that you can see at the right side of the slide. Each ball here is the electron. Each circle is a photon. Electron, after interaction, comes to one specific bin. In this way, many electrons form a distribution in bins, which looks exactly the same as in interaction between electrons and photons. Everything we talked till now is correct for the specific type of light, which is called thermal light. The thermal light is light emitted by sun, lamps, or candles that we can see every day. Now we managed how to make electron and thermal light to interact. And we can move to the next step and discuss how completely another type of light interacts with electrons. Specifically, we consider coherent light that is emitted by laser. What we found in our research is that electrons interact differently with thermal and coherent light. While thermal light really behaves as a Dalton board, as we discussed, for coherent light, completely unexpected thing happens. Electron cannot decide what to do and do everything simultaneously. Such actions are possible only on quantum level and contradict to our everyday intuition. Due to this quantum effect, the resulting energy distribution is completely different for coherent and thermal light photons. Let us now see how it really looks in the experiment. Here you can see the specific structure inside which electron propagates. If we shine with the thermal light on the structure, electrons travels as a single particles, like many separate cars on the road. If we shine with the coherent light, electron has a few positions simultaneously and travels like a train with many linked together carriages on the railway. With the specific devices, we measure real electron energy spectra, and these spectra are very similar to these toy models, what we discussed before. We see that the light with different quantum properties have different electron energy spectra. We are the first who measured this. Now, when we know how the spectrum looks, we can understand whether it was coherent light or thermal light. Thus, these spectra are the fingerprints which help to identify the quantum properties of light. At this slide, I would like to thank all our group that works as a unite team on different directions that together try to understand electrons, light, and their interactions better. We saw that electron microscope already can bring us to the quantum realm of matter, giving us possibilities to study vaccine of nanoparticles, viruses, bacteria, different materials, and its atomic structure. What our lab is working on is to make electrons to help to investigate quantum world of light, where supersensitive measurements, secure communications, and photonic quantum computers are possible. In a simple words, we want to shed some light on light by using electrons. Thank you for the attention. If you have some questions, I will be happy to answer.
Thank you, Aliaksei. That was lovely. That was very interesting. Thank you for shedding light on light. Are there any questions? I'm just scrolling through.
Hi, yeah, I have a question, please. So you said that that shedding light on light may have some really interesting outcomes regarding sensitive measurements and communication. Could you elaborate a little bit on this link? I mean, how would understanding better the light itself has such important implications?
Yes, thank you, Michal, for the question. I want to say that light have classical and quantum characteristics. Classical characteristics, it's what we usually see in everyday life. It's color of the light or spectrum, in other words, polarization and intensity. How bright do we see this light? But there are completely different properties of light, which is called quantum. And it's connected with photons and the links between these photons. And the method that we suggest here is exactly to study these links that before couldn't be studied with electron microscope, and to really image these links, which is very hard to explain and very hard to imagine with electron microscope, and bring intuition for these miracle quantum properties that people now want to use for the communication and sensing and all other these exciting applications.
Thank you. Are there any other questions?
I just want to say that the presentation was very, very nice. You do it very good, and I very like the animation, the pictures, everything was very cool and very, very understandable and approachable, even when I'm not from the field.
Thank you, Israel. You're also from the field because you're also doing engineering. So
now we transition to optical component, but until now I didn't touch this field at all. But it's very cool.
Thank you.
I would agree with Israel, he is closer to the field than I am. But I do agree with his comment that you used very good imagery and an explanation that brought it to a general audience very well. So thank you, Alex.
Thank you.
Okay, if there are no other questions, just one, I'm giving one last look. Okay, then I will thank you very much, Aliaksei. It was lovely.